Okay, let's begin. So this was the example I for you to do last time, and I also asked you to try this while I'm setting up. So let's see how it goes. Just jump right back into it. So for D, what did you guys do?
Could you break up the sines into two sine squared x? And then switch them all to cosines? Sine squared x, cosine squared x.
And then do what?
And then change change both of those to half 1 plus cosine 2x.
The half angle formulas?
Yeah.
Okay, so what is that going to end up being? So I'm going to half here, half here, half here. It's 1/8. And this would be 1 minus cosine 2x squared. So 1 plus cosine 2x. Which is going to be, well, this is 1 minus cosine squared 2x times 1 minus cosine 2x. So that's going to be 1 minus cosine 2x minus cosine squared 2x plus cosine 2x times cosine squared 2x. Minus cosine 2x. This one again, I do use a half angle formula. Are you guys doing it so far? You getting the same thing? Huh? You guys see what I'm doing?
Professor,
Yes.
how do we go from 1 plus cosine 2x to 1 minus cosine?
Well, I kind of wrote one at the back. So I looked at 1 minus cosine 2x and 1 plus cosine 2x. That's the difference of squares. So if I multiply two of these, I would get 1 minus cosine squared 2x. And then I'm left over with an extra factor of the 1 minus, because there were two of them. That brings me here. And now I'm just multiplying out at this point. And the hope is it's going to stop at some point. And there was something I could have done here. I'm not exactly sure would have ended up shorter though.
What, sub for the cosine squared x instead?
Huh?
No, because that would just give you back
Oh, wait,
cosine
no,
with a
no.
different sign.
No, I mean using the sine double angle formula. And whatever, we're already going. Because this product is going to be a lot of trouble. It might be a nicer way to do this. But even if I do what I was thinking of doing there, we'd still kind of end up here. This one's on. Did I write the wrong power somewhere? So this would end up being 1/2 over here. This would end up being, because I'm taking this 1 minus 1/2, goes here. This one I'm just copying back, leaving this one, and plus 1/2 cosine 2x plus 1/2 cosine 2x cosine 4x. I want to keep these.
Could you pull that board just a little bit down? Perfect, thank you.
That's going to be annoying, because what I would do is I would change that cosine 4x to cosine 2x's using the addition formula.
Wait, what?
So so far, each of these are easy to integrate, right? How do you deal with this product? There's actually a nice formula that I could apply here, but you don't actually do that. Kind of be unfair for me to apply it here.
Is it like not a Calc 2 formula?
No, it's a pre-calc formula, but we don't teach it here for some reason.
Can you apply it in
What the heck? Let's actually just do it. Because I'm not feeling actually multiplying that out. Here's something useful. There's something called the product to sum formulas. Which technically is kind of, if I had to multiply out, it's kind of what I would be doing anyway. So we know that, for example, cosine of A plus B is equal to cosine A cosine B minus sine A sine B. And if I were to take cosine of A minus B, this will be cosine A cosine B plus sine A sine B. Now it turns out if I call this equation 1, call that equation 2, I can actually add both of these together, right? These guys are going to die. Here I would have 2 of these guys, which I can just divide by 2. So I'm going to have 1/2 cosine A plus B plus cosine of A minus B. And over here I would have cosine of A cosine of B. Right? So this is one of them. You have like 4 of them, right? So I just proved the one that's useful. So this is called a product of sum formulas. Notice that I go from a product of cosines to a sum of cosines. Well, if you look at it the other way, it's the product of sum formulas. If you look at it this way, it's the sum of product formulas. They're kind of the same thing. So I can replace that. Just think of A as the 2x and B as the 4x. So what would I have by applying that? Well, 1/8 times 1/2 minus cosine 2x minus 1/2 cosine 4x plus, like these two I can combine. minus 1/2. It takes care of those two. This one, I'm going to apply that. So this is going to be 1/4 cosine of adding those two, 6x, plus cosine of subtracting those two, 2x. And at this point, integration is easy. So this is 1/8 times x over 2. This is going to be 1/4 sine 2x. This is going to be 1/8 sine 4x. This is going to be 1/6 sine 6x. This is going to be 1/2 sine 2x. Plus.
Professor,
Yeah.
can you please explain the 1/2 minus 1/2 cosine 2x?
Oh, this 1/2 here is from this. I have minus cosine 2x
Yeah.
and plus 1/2 cosine 2x.
Okay.
So that's minus 1/2 cosine 2x. That's this one. So I added these two here to get this one. Then there's 1/2, and there's this guy, and then there's this guy. I use that. But technically what I would have done if you don't know the product of sum formulas, I would have just actually looked at this as cosine 2x plus cosine 2x. Cosine of 2x plus, and then expand with the addition formula, recombine everybody. Eventually you'll get here. Yeah, that's stuff. So yeah, once the powers are even, things can get crazy because you're applying these double angle formulas, you have to multiply out. So that was that. What about the last one that I wrote out? Ideas here? Yeah, exactly.
You leave a factor of cosine out, and then let u equal to sin x.
Huh?
Let u equal to sin x.
Okay. So you're going to want to change this guy then?
Oh yeah.
Right. So that's 1 minus sine squared of x times cosine of x over the square root of sine x dx. At this point, a substitution of sine would be give us what we want. So you can say u equals sine of x, or if you're really cool, equals u squared equals sine of x. 2u du is equal to cosine of x dx. So this guy would become 1 minus u to the 4th. The cosine dx would be 2u du, and then below here would be u. That would cancel. So we get 2 times 1 minus u to the 4th du. And my u was the radical of sine. So that's that. So let's move away from sines and cosines. Don't feel like giving them for a week after this fiasco over here. Let's talk about the secant tangent cases. deal with the integrals now, the second form of integrals. We're up secant to the m, tangent to the n. Now there are actually three cases for these here. It's one. M is even, greater than or equal to 2, tangent present. Case 2, N is odd, secant present. Case 3. Everything else. Okay, so we're going to deal with these three cases. Now let's look at case 1. Let's say you're in the situation where you have an even power of secant and it's at least 2. Remember, 0 technically is even, but we don't want 0. You want to be able to actually see the secant there. So in case 1, what you can do is 1. Say the factor of secant squared. Change any remaining secants to tangents using the Pythagorean identity. So we know that 1 plus tangent squared equals secant squared. Third, you're going to do a substitution. U equals tangent, your derivative is going to be that secant squared. And now, after that, you're going to integrate. Example of that situation, where I want to click here.
Sorry, this is greater than or equal to 2? M is even
Yeah.
greater.
M is an even number greater than or equal to 2. Something like secant to the fourth. This one coincidentally works out. Maybe it's more of a case 3 kind of example, but so they're these two. Although the first one might be a more of a case 3 example. So this is one it turns out where you can actually save a factor of secant squared, and it'll actually work out fine because here you can get a tangent out of this one. So you can still get away with your u equals tangent. Your du is of course going to be that secant squared dx. So you get integral of 1 plus u squared du. And that's all. these relatively quickly because probably case 3 is the case I really want to actually go a little bit slower with, and also the next topic after this. I really want to get to that. Let's just jump into this. Oh, same idea. Power of secant is even is greater than 2. There's a tangent around, which means a u equals tangent substitution can work out in our favor. Same thing I'm going to do is say the factor of secant squared and put this at the end. Change all remaining secants to tangents. Equals tangent. Your du is going to be that secant squared. So you end up with the integral of 1 plus u squared times u squared. And 3x over 3 plus tangent of 5x over 5x. Give you these two. You guys can kind of finish copying. So in case 2, you have an odd power of tangent and you can see a secant out there. Here's what you are going to do. 1, you're going to say the factor of secant tangent. Change any remaining tangents to secant squares. To the secants. Again, using the Pythagorean identity, 1 plus tangent squared, secant squared. We're going to now do equals secant. Your du is going to be secant tangent, which is the factor that you saved up there. And for example, those two. Okay, so I see problem C, power of tangent is odd, there's a secant around, so I'm just going to actually save a secant tangent. This is going to be left with tangent squared, secant tangent. I'm going to change all the other tangents to secants. Tangent is secant squared minus 1. Then do a u equals secant. D is going to be secant x tangent x to x. That's your integral. And u cubed over 3 minus u plus c. That's that answer. So again, secant cubed, tangent cubed, power of tangent is odd. So we're going to say a say the factor of secant tangent separately. Going to change all remaining tangents to secants. I'm going to do u equals secant, du equals secant tangent. This means get a u squared times u squared minus 1. This is u to the 4th minus u squared. Just, as you can tell, I'm just dying to get this over with. Okay. Secant to the 5th over 5. Secant cubed over 3.
We would have let you get away with it.
Huh?
We would have let you get away with it, honestly.
Yeah. That's actually the secret. See, a lot of students don't know when to stop studying. People often stop studying too early. Here's how you know when you should stop studying. When you're getting everything right and you're just bored to death getting it right, you've studied enough. That's how you know. A lot of students, they try a problem, they got it wrong, they try another problem, they got it wrong, they try another problem. They try like 10 problems and they keep getting them wrong, they get the first one right, yes! I understand now, and they walk away like they got it in the bag. You know, I feel really good about this test. Never mind that they spend 90% of their study time failing. 10% of the study time getting things right, but they're so happy that they got it right. There's, you know, feel pretty good, man. I did okay, you know. Then you go to the test and curveball, and it's like, oh. No, you're not ready until you're like bored. You're like getting problem right. Is it? Do I really have to do more of this? I got it. That's how you know. Then you've studied enough. Before that point, no. Okay. Let's, case 3. Pretty much everything else. So here's how you deal with case 3. Like everything else. What do we do with everything else? That's not just the case 3.
Yeah, sorry to interrupt. So if you have case 1 and case 2 true together, is that part of case 3, or is you just take the case 1? Like if m is even and n is odd, if they're both true.
Probably what I would do is I would let the higher power choose which one to do. So in that case, either one would work, but you'll notice that if you do one of them, it would leave a higher power behind than if you do the other one. So I kind of made the choice based on that. Similar to how last class, Monday, when we had both sine and cosine was odd, you always go with the smaller power because it makes things nicer. You'd apply the same idea. So both could be true.
But here
Apply
you
the
go
one
with
that
higher
gives you
power.
this. What?
But here you go with the higher power?
What if I don't believe in higher
When the power of tangent is odd and the power of secant is even? You mean something like this?
Yeah.
power?
You'd start with the higher power?
I'd probably go with the based on the higher power. I'd try to lower that. So if I can save a secant squared, I knock off 2 powers as opposed to knocking off like 1 power from the other one. You see what I mean? But I think it's, I don't really find a nicer way there.
Okay. Thank you.
So I'd probably opt to get off a secant squared to knock down the powers a little further, but I don't really think there's going to be a big deal here. Case 3 is the interesting one. So here's the strategy for case 3. So step 1, you're gonna try something. And then 2, hope it works out. And 3, if not,
Unfortunately.
try something else. That's case 3.
So
We're not in Calc 1 anymore, kids. Life isn't always just so simple anymore. It turns out all other cases where you can actually get off a nice secant squared or a nice secant tangent and everyone else has even powers or you can use the Pythagorean identity, it can actually get quite tricky after that, where all sorts of strategies would have to come into play. So you'd have to really be abreast with your trig identities and all the previous integration techniques that we did. So let's do some examples of this guys.
Would case 3 be like the opposite of the one we just looked at, like it was secant 4 tan 3? Would it be secant 3 tan 4? With the minus
Secant cube tangent 4.
Yeah, would that be an example of case 3?
I don't know. What would you do in that case?
try something.
You try something. What do you think would work? I had some planned examples.
Start with the secant.
A, C, D, I think we're E. Tangent cube. Secant cube. I don't know, maybe we can add this one. Let's hope it doesn't like go like the first example we had and it takes like forever. But we can try. Okay, E. Okay, go, try some. What do you think? Give me some ideas.
Pull out 10 squared. Change it using Pythagorean identity. Kind of really off past
And what do you want to try?
that. Change 10 squared, yeah. To really secant squared minus 1.
Then?
Sub u for 10x.
The minus one messes
Yeah,
that
it
one up.
does.
Right, because your d would be secant,
Yeah.
but you have a secant squared minus 1. d would be secant squared. So what do you do in that situation? So you're now u equals u equals tangent substitution didn't work on that part. So just think of it as two separate integrals at that point. So your u equals tangent is going to work here. Your d is going to be the secant squared, so you're going to get u squared over 2. So this is going to be tangent squared over 2. Integral of tangent?
ln of secant x.
No.
Absolute value.
Ln of absolute value of secant x. Alright, that was one of the rules you had to memorize last time. Yeah, see, you tried something, it worked out. So we didn't even read step 3.
Wow.
Well, I just, meh. Hey, it worked out. Can't complain. Let's try the secant cubed. Tangent cubed wasn't so bad. Hopefully the secant cubed isn't too bad. Okay, ideas. Try some.
Why not start the same way as with the secants? Into secant squared and secant.
It's okay. Secant squared. Alright, we're gonna try.
So this is 1 plus 10.
1 plus tangent squared. These guys are applying the same. Hey, it worked out last time. Why not? Okay. So secant x plus secant x tangent squared x.
Split those into two integrals.
Split what? Oh, okay. So you can do the secant by itself, and that. What are you going to do with that? We know this. We know. We should know a general form for this since last class. Right. So that's ln of absolute value secant x plus tangent x. So don't even worry about that. What are we going to do with this guy?
If you substitute it again, you'd be going in circles, right?
Substitute what?
Tangent squared of x.
With what?
With the identity. You just reverse the original. Oh, unless you separate it again.
So if you break this up, this is secant cubed. This secant squared. It's going to be a secant cubed after you multiply out. Minus 1. So that's going to be a secant cubed minus the integral of secant. What's going to happen now?
Still need secant cubed.
So this goes away.
Yes.
Not wrong! You see what I mean about case 3? You see what I'm telling you? Okay.
I mean, it's not.
Something that made complete logical sense, but like, why wouldn't this work? Again, like, why not?
Okay.
All of a sudden, like, your plan goes out the window. If I were to give you a strategy for case 3, it's going to fail. Like, trust me. Okay? You have to be a little bit more ingenuity. So yeah, that wouldn't work. Yeah. Valiant attempt, great attempt, good first attempt, but nope, no dice. Yeah.
If you were to separate secant and then secant squared x, can't you do integration by parts?
Can't you just take the integral of secant squared?
Secant and then secant squared x, and then do integration by parts. Because secant would be secant squared would be dv, and v would be tangent.
Aren't both secant and secant squared
Integratable.
integratable? I don't know how.
Integratable. I think the word is integrable. Yeah. So we want to do it by parts. Now, the interesting thing is here, we have two of the same kind of functions. Right, these are both t squared. How did you want to make the choice?
Power.
Secant squared x be the one that's integrated and the other one differentiated. I mean, we do have the integral of secant x, but how useful is that?
Okay. So the du would be
Secant x
v would be tangent. So this is equal to u times v minus the integral of vd.
Oh, and that's the next example.
What?
That's the next example. That integral.
Yeah. That's
Oh,
it. That so we're solving G anyway.
How is it better?
What do we want to do from here? You'll see why it makes sense that that's the next example. It's going to be really cool when the time comes.
Pull out secant x tangent x. Separate that from the secant x.
But then you'd be left over with a tangent. What are you going to do with that?
That's
Yeah?
Tangent square x to secant square x.
Does it feel to anyone like you've been doing this?
This is circling.
Like, dude, I feel like we tried this before and it totally like didn't work out.
This is a circle.
Yeah, they're gonna cancel out.
This is the same thing we just did.
Hold on a
Cancel
second.
out.
They didn't cancel out. These guys are actually here. This guy I know. What happens to this guy?
You add it back to the original, and then you get
It's the guy on this side. Move this over, you get two of them, then you divide by 2. And of course, this would be the integral that is ln of secant x plus that's the answer. By the way, this is actually the traditional way to do the problem. Like if you actually look in the average math textbook that actually solved this integral for you, this is the way they would have done it. It's actually integration by parts. Who would have thought?
You would have thought, yeah.
What is the last part? How did you get from that to that?
Oh, I added this to both sides.
so you get 2.
So if I move this over, so then I get 2 times the integral, and then I divide it by 2. That's where this half came from.
Okay, got it.
So then there's secant x tangent x, and then the integral of secant x is this thing. Now, if you think that was surprising, here's the next surprising thing. It turns out that this integral actually shows up more often than you would think, to the point where it's actually highly recommended that this is now one of your basic rules. Remember that integral. The integral of secant cubed, you should know, is 1/2 secant x tangent x plus ln of secant x plus tangent x, excuse me, didn't get plus c. That's something we know now. It's one of those things that pops up in random places, like e and pi. They just pop up, like an integral of secant cubed just pops up out of nowhere.
Surprise.
It's like, what? Like you're wearing this robe, secant cubed, like what's going on? It happens all the time. Surprisingly. Like, so it's actually just something you should just know. Now let's actually look at the next example, which we said it kind of showed up here. So you do get a little bit of insight here. But as you can see, the secant cube versus integral of tangent cube, radically different approaches to these two integrals. That's case 3 for you. Just try something and you see what works out. Try something.
The question is how big time will your waste?
At this point, I'm scared to try something.
I mentioned, yeah, we did this before. So it actually ended up with one that we already solved, which is the integral of secant cube x dx, and the other one was the integral of secant x dx.
So you're going to write this like that.
Yeah.
Is it the same thing but without the half?
And since we know what and since we already solved the integral of secant.
Right, so now we actually know this.
Yeah.
So this was a fair quiz problem. If you didn't know that, this is going to be annoying. Because then try to do that while having this guy tagging along isn't really going to be fun. But now we know this one. It's 1/2 secant x tangent x plus ln of secant x plus tangent x minus ln secant x plus tangent x. See? And of course that kills that. So it's actually 1/2 secant x tangent x. Pretty cool how that worked out, I think. Everyone want to actually.
Wait, can you explain how you get the second part?
What second part?
The second, like after the basic rule that we were supposed to know, we did another.
Yeah, this is also basic rule. Integral of secant
Oh, okay.
is that.
Got it.
And the integral of the secant cube is this. But with the half. Actually, they don't cancel out because
Yeah, later.
So the half doesn't apply.
because
Yeah.
you can use parentheses correctly. See what happened? See what happens?
You're welcome.
Please.
And on one page.
So that's actually going to be. There's going to be some guys here. So this is plus a half minus, so it's going to be minus 1/2. Again, it's plus
Parentheses or something.
plus c. Don't forget those parentheses. Okay, so this example is just randomly thrown out there, so what do you want to do? Hey. That's your example. We're here because of you now. So what are you going to do?
That's true.
Wait, somebody else.
Okay, go. Try some. Come on.
Well, we just found out the rule for secant cube.
Okay. But it's multiplied by a tangent to the 4th.
Why don't we change the tangents to secants?
You would change the tangents to secants?
Oh boy.
Oh no.
Your questioning tone makes me question that.
No, what would you try?
I mean, yeah, I think that I would question.
Okay, what would actually happen if you do that? So tangent to the 4th, how would you change that to secants?
Do two squared, two tangents squared.
Okay.
Minus.
So you're gonna end up having secants cubed times what's gonna be secant squared minus 1 squared. So that's gonna be secant to the 4th minus 2 secant squared. Plus 1.
Are there all times multiples of 3?
Come again? What?
No.
secant to the 7th, minus 2 secant to the 5th, plus secant cubed. Hey, I know that. How are you going to do with these guys?
You don't?
Like we don't.
Yeah.
Wait. Oh,
Yeah,
tangent's
it's
not there.
supposed to turn those into integration by parts and do the same steps you did.
Yeah, you're gonna like take off a secant squared, do the whole dv equals secant squared. It'll probably work out. I don't know. Try it.
Oh.
Try it. I'm not gonna. Wait, like the moment I saw secant to the 7th, I lost it. This is BS, man.
Is that how you would start it though?
Huh?
Is that how you would start it though? Or do you think that
Can
there's
you
a
think
better
of a better
I
way?
looked up a Wolfram.
Can't you do h by integration by parts since you know secant cubed? That would be your d here. And then you can integrate that into the 1/2 secant plus L.
Yeah, and then your dv.
Yeah.
No, you're saying the secant cubed is going to be the dv,
Yeah,
but then your u would be tangent to the 4th.
yeah.
Your du is going to be 4 tangent cubed times secant squared. So you're going to take 4 tangent cubes times secant squared. You're going to end up multiplying by that. I mean, I don't know where that's going to go. Try it.
Let's go look at Wolfram.
And tell me what you come up with. I want to move on with the plan.
Thank you.
So, like I said, the rules for cosecant and cotangent are super similar to the rules for secant and tangents. So we're not going to do those. We're not going to ignore those guys. But I actually want to move on to something. So yeah, try to actually do this. Tell me what you come up with. I'm interested to see who has the most creative solution.
Will we get extra credit?
Yeah, sure.
What does it do to you?
Huh? I actually want to move on to, I believe it's, I want to say 8 1. I want to another section. We are going to talk about trig trigonometric. Right, we always say this. Substitution. So there's something called trig substitution, which is kind of like substitution but a lot worse. So here is the idea. We know a lot of nice trig identities. In particular, we know about the Pythagorean identities. We know about things like 1 minus sine squared equals cosine squared. We know that, say, 1 plus tangent squared equals secant squared. We know, say, secant squared minus 1 equals tangent squared. Let's use status instead.
Foreshadow.
Yes, it's fortunate. Because I'm going to switch back to x's. Right? Now, with these guys, we can say multiply both sides by a squared. So if you have a squared times a sine theta, that collapses into a squared cosine squared. And of course, if you have a squared minus a tangent theta, that's going to collapse into a secant squared. A squared secant squared. And if you have a secant theta squared minus a squared, this is going to be left with a squared tangent squared. And here's how we're going to make the equivalence here. What if instead of these trig functions, I just had some other function? So you notice here, so call that x, right? Or the Roman numeral 10 if you fancy, right? But the idea here is there is some sort of equivalence with seeing something like a squared minus x squared. Somehow that seems equivalent in your mind with seeing 2 cosine squared. And if you see something like, it should be a plus. If you see something like a squared plus x squared, you can draw an equivalence in your mind with a squared secant squared. And if you see something like x squared minus a squared, there's some sort of equivalence in your mind with a squared tangent squared, right? So these expressions here kind of have some sort of meaning for you. Here's the nice thing. Notice that there are 2 terms here and only 1 term on that side. So kind of like taking an idea from the trig identities, how they can collapse 2 things into 1 thing. If I'm in a situation where having 2 things is a problem, and in particular, they look like this form, like an a squared minus an x squared, or an a squared plus an x squared, or an x squared minus an a squared. If I have one of these 3 forms, I can think of the x as a particular kind of trig function. That if I were to substitute the x for that trig function, it's all going to work out a lot nicer. So here's how, let's make this idea a little bit more precise. This is kind of where the idea is coming from, kind of gooey at this moment, but let's actually make it more precise. Here's the trig substitution idea. So, to formalize. There are going to be times where you're going to be seeing a certain expression. Okay? And you are going to want to make a certain kind of substitution that is going to turn this expression into something more convenient. So, for example, there are times when you're going to see things like a squared minus x squared. And it shall behoove you to say, think of x equals a times sine theta, right? Because if I can put in a sine theta here, I can use the Pythagorean identity to collapse this into 1 term, right? Particularly useful if there's like a radical over this, right? Radical of a sum, very hard to deal with. But if I throw in a sine in here, it collapses into the radical of 1 thing, right? So you can do this guy. And of course, some useful formulas. Now, once you pick your a equals a sine theta, it turns out that your sine theta would then be x over a, which would give you the fact that you could actually create a triangle. We're going to put this all together pretty soon. Where the opposite is x, the hypotenuse is a, and then this would be a squared minus x squared. We're going to see why that's useful, but that's just Pythagoras, it's not a big deal. So there are times when this expression is going to lead you to wanting to do this substitution. Once I plug that in, it's going to turn it into a cosine squared, which is going to be nicer in a lot of cases. And I can use this triangle to figure out any other trig functions that might show up. Similarly, I can have x squared minus a squared. In this situation, x equals a secant theta would be a nice substitution. Why? Because if I do that here, you see that it will change these 2 terms into 1 term. And of course, this would mean that your secant theta is equal to x over a. So you'd be able to get a triangle where this would be adjacent over hypotenuse. Hypotenuse over, it's secant, so it's hypotenuse over adjacent. And then this would be square root of x squared minus a squared. A third scenario that will often show up is the sum of the squares, x squared plus a squared. In this situation, a tangent theta seems very natural because it would remind you of the second line over here. that will transform this into one term, namely a squared secant squared. And of course here we have that tangent theta is equal to x over a. So this triangle becomes useful down the road. Opposite over adjacent. So this is going to be the radical of x squared plus a squared. And essentially that's the technique, really. Making these substitution will often simplify it to a different kind of function. So this here that's essentially that. So basically, the table you sort of need to memorize. The first two columns you should definitely memorize. I think this last column you'll be able to figure it out when the time comes, but at least these two. You should now have an equivalence in your mind between a squared minus x squared and x equals a sine theta, and x squared minus a squared and x equals a secant theta, and x squared plus a squared and x equals a tangent theta. These should be equivalent. So you should have these connections memorized. Okay? And now, some of you might be wondering, what was wrong with good old substitution? Like, why do we have to make it all complicated? We substituting trig functions. Okay, let's do some examples. Which will hopefully get you to appreciate the value of these substitutions. Now I know you automatically know what that is, but let's actually derive it from scratch using that method. Let's see. We're not going to get through all of these, but whatever we don't finish, you are going to finish up for homework. Square root of 3 over 2. Those are all examples. By the time we get through those, we will be well versed in the virtues of this section called trig substitution. And it's called trig substitution because you're substituting a trig function into the expressions. Some time to copy those down, and then we'll work look at a few of these examples.
That last one is 3/2.
Here?
Yeah.
Yes, it's the raised to the power of 3/2. I think we're all just about done copying down here. So, show up on the quiz on Monday, that problem pops up. What do? It's your first stop. Huh?
Change the bottom to A something.
That would be your first stop?
Draw a triangle.
Yeah.
Draw the triangle would be your first stop?
2 squared minus x squared.
First thought, always, is it a basic rule? That's the first thought. Second thought, can I simplify it to look like a basic rule? None of those are going to pan out. Third thought, can a substitution work? Can a substitution work? Can a regular substitution, old-fashioned substitution, the ones we're used to? Why not? Why wouldn't a substitution work? What would you want to substitute?
Square. Actually, the radical.
You'd want to
4 minus
substitute.
x squared.
The entire
Yeah, you want to substitute for.
Like u equals 4 minus x squared, right? Or u squared equals 4 minus x squared. What's going to happen when you differentiate that? You get 2x dx, right? You're going to get rid of one of the x's. You're going to have one x left over. What's going to happen to that x? Well, if your u equals 4 minus x squared, you solve for that x, you're going to get this whole other radical. You're pretty much going to end up in the same sort of situation, essentially, right? Because if you say u equals this, solve for x, what's going to happen? Well, it's going to be 4 minus u, all the radical, and it's not going to work out, right? You can try it, well, don't try it now. You try the substitution. The problem is you're going to have one of these x's left over, which if you try to solve for that x, you're going to get this whole other radical expression. It's not going to actually work out nicely. Right? So, what seemed almost obvious in this situation, which definitely is substitution, come on. Now that's not so clear. So, you look at that, you think, can a substitution work? Now you realize, oh, we have an x squared, so the substitution is going to get rid of one of the x, I'm going to have an x left over. It's going to put a radical inside this thing that's already pretty messy. So, now what you notice is that this 4 minus x squared here can actually be thought of as one of those expressions. Which one?
A squared minus x squared.
The a squared minus x squared. This is like 2 squared minus x squared, right? Your a is 2. So now what you would do is you would say, hey, let's try to use that substitution. So just plugging in a u substitution isn't quite going to cut it. So what I'm going to do is instead plug in a sign substitution. I'm going to set x equals 2, because 2 is a, sine theta. Now let's see what's going to happen with this. dx is going to be what? So now I'm going to go and I'm going to plug that in. Now of course my x squared on the top is going to be what? Well, 4 sine squared, right? My dx is going to be 2 cosine theta d theta. What's going to happen under here? Well, I'm going to have 4 minus 4 sine squared theta. Right? But that's actually a nice expression. That's actually just 4 cosine squared. So the denominator here is really just 4 cosine squared because of the Pythagorean identity. So now I'm in a situation where I went from 2 things under the radical to 1 thing under the radical. Well, what's this going to do? Well, it's going to be 2 cosine theta. So this whole thing is going to cancel that whole thing. And that's the integral now. Can we do that integral? Yeah, so that was from the last section. How do you do that integral? 4 sine squared. Double angle formula. What's that going to look like? Huh? Applying the double angle formula to this is going to be what?
Cosine theta,
2
4 cosine theta, sine theta, d theta. What am I?
It's a sine squared. Well, how do you change the sine squared? Right. That's the formula you guys should have memorized last time. Sine squared is 1/2 times 1 minus cosine 2x. And cosine squared is 1/2 times 1 plus cosine 2x. So I can do that. Now, integral of 1. Theta is d theta. Integral of this, 1/2 sine theta. So you can actually find an integral here. Now here's the problem. That's an answer in thetas. How do I actually get an answer in x's?
Take the inverse sine of.
Can't you?
So that's going to be an inverse sine. What is that going to be? How do I change this expression to x's?
That was a triangle cosine theta.
That's where the triangle is going to come in. That's going to be useful. So here's what we're going to do. To actually do the back substitution here is going to be a little more annoying than a regular u substitution. Because to change back to x's, I have to find a way to convert those trig functions back into x's. So now, since here my sine of theta is equal to x over 2, this means that I can construct a triangle. Opposite over hypotenuse, this is going to be the square root of 4 minus x squared, which means my cosine of theta is going to be adjacent over hypotenuse. And I also know that sine of 2 theta, hopefully we all know, is 2 sine theta cosine theta. So this expression here is just going to be cosine theta sine theta. And I can replace the cosine with that expression. I can replace the sine with x over 2. I can replace this now, of course, with arcsine. So this here, of course, means that your theta is going to be sine inverse of x over 2. And yeah, so this means that my original integral is going to be equal to 2 times sine inverse of x over 2 minus the radical of 4 minus x squared times x over 4. That's the answer. That is a trig sub. Now, of course, as you can tell, so you're going to do this trig sub. You're going to get some expression which is trig functions. Now, based on what we did in section 8.3, you should know how to handle the trig function. You're going to get an answer in terms of the trig functions. Now, that is, you're kind of not right up on the answer at that point. At that point, now you're going to have to figure out how to change the trig functions back. Which means, remember the strategy, you would think substitution before you have to do something like this, right? Because if you don't have to do this, a lot of time is going to be wasted here. Right? In fact, every situation where you, in the situation like this, the x over the radical of 4 minus x squared, a regular substitution is what you would do, but it turns out a trig substitution would also work, but it would take a lot more time. So you don't want to have to do a trig sub unless you really have to. So you have to be very careful to actually think, could I get a u substitution to work here? Now, more than likely that was probably a little bit weird for some of you, which is why we have tons of examples to get you used to this idea of like infiltrating something with the trig function. So let's just move on to another example. Should be a little bit easier. So let's say hell freezes over and you forget that that's arctangent plus c, right? Let's say that, right? Of course, you would never actually forget, but let's say you forgot. How can you figure that out from scratch? Well, a substitution wouldn't really work. U equals 1 plus x squared, because my d is going to be that 2x, and I don't have any x's to actually get that substitution to mingle well here. So the other option is to notice that, hey, that's actually 1 squared plus x squared. So that reminds me of one of these forms, the a squared plus x squared, which means there is a convenient substitution to put here, which is x equals tangent theta. Now my dx is going to be secant squared theta d theta. And I'm going to actually now plug that in. So this integral is going to become 1 over 1 plus tangent squared times my dx is secant squared. And how can I do this integral? One plus tangent squared is secant squared, right? Remember, the whole point of doing this substitution is to get these two terms to collapse into one. So that cancels that. You just have the integral of 1 d theta. What's that? Theta. What's theta? Well, if x is tan theta, then theta must be 1 tan inverse of x.
That wasn't that long.
Hmm?
That wasn't that long.
Don't forget what that is, though. Don't be like, I'm allowed to forget this now, because I could just do this and like confuse. Like, no, don't forget. Yeah.
Can you go over that last part? How'd you get tan inverse? The last part?
Because x is tangent theta. So I take the tan inverse of both sides to solve for theta.
Oh.
Let's look at example C. course, that guy looks pretty annoying. I do want you to take some time to appreciate that it's not a basic rule. You can't really simplify that to look like a basic rule, and a substitution wouldn't really work out for you. Right? Because you'd want to substitute u equals x squared minus 3, but your du is going to have an x in it, and that's just not going to work out very nicely. And before you sneakily kind of think, well, I can throw an x in there, right? Just multiply by x over x. Well then, deal with x cubed when your u is x squared plus minus 3. That's not going to be nice. So, a substitution is not going to work out nice for you. But you should think about it. So now that we realize that a substitution really isn't the way to go, give me another option.
You got x squared minus root 3 squared.
Right.
To the radical.
So,
Secant.
x equals,
Yeah.
A secant.
Or
Rad 3.
a secant theta. Is that actually going to give me something we can do? Well, let's see. The dx would be derivative of secant theta, tangent theta. So I go and I plug this in. This is 1 over x squared. X squared would be 3 secant squared. X squared minus 3. That's actually going to simplify into 3 tangent squared. Take the radical, I would get radical 3 tangent. Times, I have this radical 3 secant theta tangent theta d theta. This cancels that, this cancels that, this cancels that. So that's all simplifies, this monstrosity simplifies to that. How do I integrate that?
isn't that just cosine?
That's just cosine. Integral of cosine. Positive sine. So that's actually the integral in the theta universe. How do I get it to be in x's?
You have to use the triangle, right?
Alright, so here I know my secant theta is equal to x over radical 3. So I would have a triangle where this is hypotenuse over adjacent, which means that this is going to be the square root of x squared minus 3, which means my sine theta is opposite over hypotenuse. So this means it's just 1/3. That's the integral. So that Trig Substitution. So obviously, by the time you want to attack this section, you need to get really bored with the trig section, right? Obviously. So, because ultimately, once you do this substitution, you're going to get an integral that's going to have a trig in it, and potentially a secant cube might pop up out of nowhere. Who knows? So you need to be very well versed in trig integration in order to do the trig substitution, because you really go from a situation where there are no trig functions to where there are trig functions. But hopefully, having the trig function is going to be easier than attacking the original problem. All right. Let's see who's got their thinking caps on. This one. Or maybe it's too close to bedtime to have a thinking. Dude, I'm about to wind down. Like, this is not when I do my best thinking. Yeah.
Separate the 8 into 4 and 4. Not factor? Yeah, that's the word. Into x plus 2 quantity squared, and that's your x value, I guess you could say. Because you could consider that as 1.
Alright, so this is, to write it in this form is what we would call completing the square. You can think of that way too. So what you just did was completing the square.
Yeah.
So yeah, those two are actually the same thing. And now what?
You have 2 squares under the radical. x squared plus k squared.
So what would, how do you
X
confuse it?
equals a times
Huh?
What is it, x plus 2 is equal to 2 tangent theta?
Right, because the x plus 2 is like the x,
Yeah.
right? So that's your variable. Differentiate both sides. And now we're going to start plugging in. So this will all be 4 tangent squared plus 4. That's going to simplify to us 4 secant squared, and then you take the radical. So that's the denominator simplifies to 2 secant with this substitution. Then your dx is going to be this guy. 2 times secant squared d theta. These guys cancel. This is just the integral of secant. What's the integral of secant?
ln absolute value secant x. There's theta.
And now you're going to want to change those guys to x's. So from here, we know that our tangent theta is actually equal to x plus 2 all over 2, which means I can have this triangle that's opposite over adjacent, and this is going to be the square root of this square plus that square, which is actually just the original thing. Actually. So with that, now write this in. Equals. So it's going to be ln of the secant. Now secant is going to be hypotenuse over adjacent. And tangent is going to be opposite over adjacent. Now, I can tell you one thing. If this were a textbook problem and you look at the answer in the back of the book, they would not write the answer to look like that. They would write the answer to look like this. And at this point, someone explain to me, why are these two acceptable? Yeah.
Because the denominators, they just become minus ln of 2, which is also a constant, so it just becomes c.
Right, because remember that log of a over b is log a minus log b. So I have log of this thing over 2, which is just log of that thing minus log 2, and log 2 is of course a constant, so they'd absorb it into. So these two are actually equivalent. Chances are your textbook would type up this answer, not that answer. So. How are we feeling? With some practice, I'll do. Maybe we can get through another one, like
We
E.
got like 3 minutes.
Oh, let's work. We have to work fast then. All right, quickly.
You got 2x squared plus 1 squared out of the radical.
Right. So
What's it called? 2x equal to tangent theta.
So we have 2 dx equal to secant squared theta d theta, or your dx would actually just be 1/2 secant squared theta d theta. So this is actually going to become 1/2, well, it's going to be secant squared theta d theta over, well, this whole thing here is going to just become pretty much tangent squared plus 1. Which is the radical of secant squared. So that's just the secant. This cancels that. So that's 1/2 ln. Then we're going to do our whole triangle business. our tangent is opposite over adjacent, which means this is going to be 4x squared plus 1, which means my secant is going to be adjacent over hypotenuse over adjacent, so that's 4x squared plus 1, and my tangent is going to be opposite over adjacent. Justin? Do the rest of them. Have fun.
I have a question.
Yes.
Quiz on
Covers up to this,
Okay.
up to trig sub. Yeah.
Can you please explain how it went from 4x squared plus 1 radical to 2x equals theta?
Because the 4x, this is really 2x squared plus 1, right?
Oh,
And my 2x is tangent, so this really becomes tangent squared plus 1, which is secant squared. Then I take the radical. This is
so this is the A,
huh?
so this is like the A part, like A tan A.
The A was 1.
Oh, the A was 1.
So this 1 squared, that's your A squared.
Stop the way.
So it's 1.
Stop the way.